All right, well, maybe we should get started. It's 4 o'clock right now. Um, so yeah, for those of you who are here, thank you for coming to lecture 11 of CS or CSI 545, the introduction to robotics for master's students and some advanced undergraduates too. So let's see. So the last few classes, we've been covering a lot of the filtering algorithms. So like by now, you've probably gotten sick of here's the Bayes filter, here's another version of the Bayes filter, and so on. So, well, the good news is we're switching to some different topics. So, or bad news if you wanted more of the filtering stuff. So yeah, today is going to be more on mathematical programming, or you can also view it as like math optimization. So if you're taking classes like the convex optimization, you'll see some similar material, and if not, then you'll have a head start for when you do take it later. So logistical things. So homework 3 was due February 13th. So today is Valentine's Day, so that's the 14th. And then yeah, so it was due yesterday. And I see there's been a lot of comments on Piazza, so just keep asking them, and then we or particularly Shihan, one of the TA, will try to answer them. Uh, and yeah, if you do need to use late days, it's totally fine. Just remember that you have 7 for the semester. So ideally, you want to save some for like homework 3 and 4 in case you like end up getting a bunch of exams or interviews in a week. So, uh, and yeah, lab 2 is due February 25th. So I hope that's going well. I'm guessing most of you will start that after you've done homework 2, but just encouraging you to get started on that. Yeah, and then we do have a midterm, so it's coming up March 4th in class. So I'll try to make sure that we provide a lot of review material for you, like give an example question. Um, any logistical question? All right. So yeah, maybe let's get on with the material for today. So, and some of it will be a little bit of review from the linear algebra lecture, but hopefully we'll go through something in a little more detail. And if you maybe if you have like a pen or an iPad ready to do some math, maybe that's also pretty helpful for today. Uh, So today we will be talking a lot about optimization. So optimization is very important. It's a very deep mathematical field. And it's also very mature too. It's very mature, and it's also like very widely used in not just in robotics, but in many other fields like economics and other even other aspects of AI, like computer vision and natural language processing. You have different forms of optimization problems, like find the something which is the maximum of the function. So in robotics, there's different problems that we might care about. So how can a robot reach a specific object while avoiding obstacles? Or how can a robot go to its destination while minimizing energy consumption? And then the idea of optimization is to try to formalize that. So we need some kind of consistent, framework for formalizing that. And it also makes it a lot easier to specify it in code. Like when you have code, you need to be able to say, here is my objective, here are my constraints. And why do we need constraints? Well, you can say, well, if you have a robot and then you go to some destination, you could just say, well, just go to the destination, but you have like constraints, like the robot can't just go there and instantaneously. And there's things like, you might want to go there, but you don't want to use too much energy. Like it doesn't make sense to go someplace, but expend so much energy that, it's extremely wasteful, for example. So yeah, this is sort of like the motivation for why we study optimization problems in robotics. And again, not just in robotics, but many other fields. But we specifically will well, today it's mostly like a general framework, and then I think mostly in the next few classes, we'll be introducing some examples of, here are some constrained optimization problems that we use in robotics. So, formally I mean, at the simplest kind of problem that you can think of is, well, let's start with, say, a function from R to R. That just means it takes in a single scalar, then it returns a single scalar, like, or in other words, a single real number. And then if it's just one number as input, one number as output, then you can plot it, and then we can actually visualize it. And then how do you find the minimum of something? Because we frame it in terms of, minimize the thing. If you want to maximize something, then just put a negation in front of whatever you want to maximize, and it turns into a minimization problem. Yeah. And yeah, hopefully everyone has seen that, if you want to find the minimum of this function, so you can find the set of points where the derivative is 0. So in other words, that's like the slope of the function at different points on it, and then you find minima by where the second derivative is greater than or equal to 0. Is that the global minimum or just a local one? Yeah, so local. So we haven't specified that this could be the global. I mean, if you just look at this, you might say, well, yeah, sure, this looks like the global minimum, but we're just showing the function just to visualize. Like in the general case, you need to say a little more than just saying that you have the first derivative 0, the second derivative is like greater than 0. Yeah. All right. So like this is the most basic kind of problem, and again, hope that most of you, if not all of you, have seen this before. And then when we talk about optimization, we often do it in n dimension. So it's not just the real valued case anymore that's covered in like single variable calculus. Like you have an n-dimensional function. So what this means is it takes in an n-dimensional vector and it returns a single scalar. And n can be 1, it can be 2, it can be a million, or yeah, depends on whatever problem you're considering. And then if you want to find condition for a local minimum, so again, not necessarily talking about the global minimum. I mean, we might be under some circumstances, but here we're really talking about the requirement for a local minimum. And then what we need is so that we have the gradient of the function be 0. So you can think of the gradient as the vector value generalization of the derivative, but in n dimension. So we covered that in lecture 2, I think. But what we didn't really cover was that if you want to show that x star is actually a local minimum, then you need to show that what do you call this? What's the term for this? Yeah. Yeah, Hessian, right? Yeah, so you can roughly think of the Hessian as the second derivative. So it's kind of like the second derivative, but for the vector value case. Yeah. And the condition here, we write it like with this symbol here. Like sometimes we just use the greater than or equal to thing, greater than sign, but basically just think of this as meaning that it means positive is definite. So you can think of that as like in 2 dimensions, imagine a bowl-shaped function where it's like a bowl, and then the minimum is the bottom of the bowl. And if you have a function that's defined with, such that if you take the gradient twice, it's positive definite, then that the function is shaped like that near the point x star, then you get your local minimum. Yeah, so the other condition, just to be like more mathematically precise, that you do need f to be twice continuously differentiable, because if it's not, then you can't really differentiate it. So All right, so yeah, hopefully this is all clear. It's like, the vector value generalization of the single variable case. All right, so the Hessian is a very important matrix. It's the n by n symmetric matrix of partial derivatives. So if you want to write it out formally, I mean, in practice, you wouldn't. I mean, in practice, you don't usually go through the computation for every single item. You either just use some rule like that we'll cover later, like you have some rule to do it, or you just have it computer compute it. But this is like how you write it out if you write out each individual item. So you have our function f. If a vector valued function, it goes from n dimension to one dimension. So like, this first thing is you're taking the derivative with respect to x1, but you're doing it twice. And then here is like the partial derivative of x1 times the partial derivative of x2 with respect to x2 of the function f. And you can kind of see the pattern, right? Like this row has x1 the leftmost partial derivative, and then this row has x2 and so on. Yeah. All right. Everyone clear on the definition? So one thing that I think it's just a little bit, it's just kind of important to keep in mind is that the Hessian is a particular type of matrix. It's a very important matrix. The other matrix that we've been talking a lot about is the Jacobian. So this is the quick difference between the Jacobian and the Hessian. Right? So this is the Jacobian matrix, and then this is the Hessian, right? So you see the difference between the two. So the Jacobian is the matrix of like you only have one partial derivative applied on each item. But the reason why you have a matrix is because the Jacobian is applied on a vector valued function. So you need to pass in some vector, and then you get some vector as output. Now you could get it to be like one-dimensional, but it's more interesting if the Jacobian is applied on a vector value function where it takes in some big vector as input, and then it outputs another big vector. Yeah. And the Jacobian does not have to be square. Like in the lecture, I think we gave some simple examples of the Jacobian being like 3 by 1, just so we could actually write it out in the slide. Yeah. All right. Yeah, then I guess like practically speaking, the matrices are used for like different reasons. So yeah, so if you remember, like what is the Jacobian used for in this class so far? Do you remember? Yeah, yeah.
And the basically, the linearization is correctly said.
Yeah, so when you linearize things with the common filter, you get the Jacobian matrix that's part of the derivation. So that's basically what's happening here. It's mainly because when we work with, I guess like when we work with the function that define the common filter, they're generally defined on like vector value functions. So you end up getting matrices that result. Yeah. All right. Yeah. All right. So let's just do a very quick example. So you have these conditions like C is a real valued number, B is some n-dimensional vector, A is our symmetric matrix, it is positive definite. Then what's the gradient of that? Yeah. We'll go through this in a little more detail computationally, but hopefully this kind of thing, once you've seen it, then you can answer it in something like 5 or 10 seconds. I'll let you think about it for a few seconds, then we can go through it. Everyone got it? All right. Yeah. So the gradient would be b plus ax. And by the way, the gradient is with respect to the, yeah, is with respect to x here. So the, like we hit it here, but it should be, if you really want to be rigorous, you can also put the x as a subscript over the upside down triangle. So, all right. Yeah, and if you really want to go through this in a little more detail, like here's roughly how the steps work. And if you also want to think about it, you can first think about it in the scalar case where a is greater than 0. And then you have f of x be this equation here, c plus bx plus 1/2 ax squared. And then when you try to find the value of x that minimizes this function, then if you take the derivative, then the c goes away, you get b plus ax, where the 1/2 and the power of 2, they cancel out. And then when you take the second derivative, you end up getting with just the value of a. And a is greater than 0 by our assumption that we made, and therefore the x here is a minimizer. And if you set the first derivative to be 0, because that's how you find the minimum, you get x star equal minus b over a. Yeah. Is this the global minimum? Yeah. So you're saying it depends on the function? Well, we're making the assumption that a is greater than 0 here. So it so it's already a convex function. So no, it would be the global one. Yeah. Then if you want to generalize this case to the n equals 2 case, then you would you would think of this, but generalize it to the 2-dimension case. So that means x is now a 2-dimensional vector. Then you get c plus m. Because remember, every vector is by default a column vector. So you'll do the transpose, but it's going to be on column vector. So this will turn into a row vector. Then you get a 1×2 matrix times 2×1. You get a single real valued number. And then that's like the whole point here is that this is a real valued function, gives you a scalar. Even though we have matrices and vectors here, they turn into scalars at the end. Yeah, and then you get this, and then this is the matrix that we have. And if you do the math and plug in the numbers, then well, this thing turns into b1 x1 plus b2 x2 because it's just the dot product or the scalar product between the two vectors. This is how we you multiply x1 and x2 with the matrix. You do the left multiplication, then do the right one. And then because we made the assumption that A is positive definite, we only consider matrices as positive definite, they're symmetric. They have to be symmetric. So yeah. So whenever we say, this matrix is positive definite, it's square and symmetric. Yeah. And then that's why we get these two terms like x1, x2, a21 plus x1, x2, a12, they both, now you can substitute this with a12, then you get this, right? So if you want to do something like compute the gradient and then you would compute the Hessian of this, then yeah, everyone knows how to do that, right? So yeah. So this is how we compute the gradient. So I'll just give you like 10 seconds to think about it. Everyone got it? This is not graded, at least not now. Yep, so whenever you do df over dx1, then you look at this whole function, differentiate with respect to x1, and then you get b1. This term goes away. You pull the 2 down, and then you get x1, a11, and then you get the remainder of this term, but you remove x. Yeah, you would remove x2 or x1, sorry. And then the 1/2 at the beginning cancels out the 2. So you get b1 plus x1 a11 plus x2 a12. And you could do a similar algebra for the second row. And then, I mean, the way that this is written, you can split it into, this vector is the component that's from B, then this one is from the matrix A, then you get B plus AX. Yeah. So basically, once you've done this once, then you can start thinking about how this generalizes to, other cases, and then eventually when you see problems like compute the gradient of something, you'll probably skip this intermediate calculation and then go straight to the end. So, all right. So what's the Hessian? Yeah, what's the Hessian?
Matrix A, right, for this.
Just the matrix A. Oh, okay. Yeah, so when you compute the Hessian, you end up having the 2x2 matrix of the partial derivative. And so what happens is, to think about this, you can think about for the top left component, then just think of the first df over dx1, you get this term, the top of the first term of this vector, and then you apply the partial derivative with respect to x1 again, and then the b goes away, the x1 goes away, then this term goes to 0, so get a11. And then you do something similar for this. So yeah, then you get the matrix A. All right. And then, is there a typo here? I don't, is this, so there's someone saying that this is a typo, but I think they're referring to A12 and A12, but A is symmetric, so they're the same thing. You could put in, I mean, if you want, you can put in A21 here. It's a symmetric matrix. So, yeah. All right, gradient descent. So, yeah. So we have this function. It's a real value function, takes in a single number, then it gives you a single number. To find the minimum, you follow this very simple thing. If the derivative at the point x, so let's just say that this dot, and then if you just bring it down to the x-axis, that's the x value. If the derivative is negative, then you move right. Actually, maybe this is a typo. Like if the right. So if the slope is so if the this might actually be typo. Like it depends on depending on how you look at this. So I think the bigger takeaway here is if at this point the slope is the tangent line is pointing this way, then you want to move left because the minimum is to the left. Yeah. And then if you're over here, then you want to move to the right, basically. And then if you're at the bottom, then you're at the point when the derivative is 0. Yeah. Is that a global minimum? What if it's a convex function? Then it would be. Okay. But this is not a convex function because the function is not a bowl shape. So you get like this, the slope goes, it's like going up here, then down here. Yeah. So basically the idea is that in higher dimensions, you compute the gradient instead of the derivative. But the same principle applies if you find the gradient point in the direction of maximum decrease in the function value, then you repeatedly apply that until you end up stopping. So when you have a function of, from order R, then gradient descent, basically the idea is that you have some value x, and then you're trying to adjust its value so that it makes the function value smaller. And then you do this repeatedly until some stopping criteria. And the idea that you have your next iteration of the value of x here is going to be xt plus 1 equals xt plus a, or usually you'll see like alpha as the constant, or beta. So this is just some constant multiplied by the derivative f prime of x. So if a is greater than 0, then you're basically doing gradient ascent. So you're trying to increase the value. If it's negative, then you're decreasing the value. So just be aware of when you're doing like when you're trying to increase or decrease the value. Yeah. Yeah. And then what did the equation look like in n dimension? So it's kind of hard to type in Google Doc because you need the gradient term. So basically the same idea, except you have xt plus some constant multiplied by this term. Yeah. All right. Any questions on this? Well, what value should you set a to be? Yeah. What?
Probably strike a balance between like maybe like a very large value, like it should be just right so that it doesn't overshoot the minimum, but it should also not be like so large, so small, so as to like take too much time to compute.
All right. So the short answer is like it's kind of tricky to set the value because you have to balance between overshooting versus undershooting, right? Yeah. So I think there's whole like papers and studies on how to properly set the value of a, right? So in practice, if someone had done some coding and then they say, here, I use the value a equals 0.1, then you just use it, right? Yeah. So if you have a high, by high I mean like in absolute value, because it depends on if you're doing like ascent or descent. But if the absolute value of a is very big, then you cover more ground at each step, but you might risk overshooting the objective. And the same thing if you have it at a very low value. Right? Oh yeah, so when you're doing this, you have to compute the gradient, right? But what about the Hessian? So did you know like roughly like how much what's the rationale for like computing the Hessian to determine the next value, or what's the argument for and not using either for the using the Hessian or not using the Hessian? Yeah,
What I know is like, it would converge a little faster because it takes into account the curvature of the function. So it would like maybe converge in less steps, but then there's also trade-offs such as high computational costs. So
yeah, I think that's how I would describe it. So if you want to use the Hessian, it can help because it gives you second order information. So there are some algorithms that are a little bit more advanced than gradient descent, which use the Hessian as part of determining where the next value should be, but then you have to compute it. And the Hessian is a matrix, like it's n by n, so if you're dealing with like, deep neural network, then n is some very big number, right? So it can be very tricky to even get this matrix to like fit in memory, whereas like the gradient, it's only like n dimension instead of an n by n matrix. Yeah, and then, oh yeah, so this is like a nice visual. Like, I don't know if anyone has seen the 3 blue 1 brown YouTube channel. It is pretty nice. All right. Hey, a lot of you have seen it before? Okay, okay, cool. So I'm not gonna watch the whole video. It's just gonna be like, I just wanted a nice visual of like how gradient descent works. So if you look at 525, where am I? So what happens here is this video is considering the function. It's a cost function, so what he's using is the value c. I use f here, but no, c is just some cost function. So it's the thing that we're trying to minimize. The input is this big vector. Yeah, he used 13,002 just to make a point about how big the number can be. But this is actually a pretty small number, by the way. So, yeah. And then this turns into a single, oh yeah, a single input vector. Then you have some cost function, and then this is like the true minimum that we ideally want our value to go to. And yeah. And then what happened there, all right, well, I'm gonna skip some of this, but yeah. All right. So what happened here is what he's doing is basically trying to say, like, if the slope is a certain arrangement, then you move like left or right. So in this case, you would try to move like left to get to this minimum. If it's the other way around, then you would like try to move right. And the way to try to, yeah, and then you would make like iterative steps to try to, get to the minimum. If you have a big step size, then you could risk overshooting that, and then you would end up like in the very costly region of the function. And then you would sample many different, well, I guess he's sampling one item, and then you can think of gradient descent as you sample something, and then you just watch the ball roll on the function. Yeah. Yeah, so this is why gradient descent is not guaranteed to converge to like the true minimum, but don't get to go to a local minimum because there's like 3 of them. Yeah, I think 3 of them here. Yeah, and then you can also think of it in higher dimension, although the most we can usually go to is like 2 dimension, where you think of like a big complex function in 3D that describe the value of a 2-dimensional function at each point, and then you'll get some curve that look like this, and then gradient descent will basically like start from a point, move in the direction of maximum decrease, and then repeatedly apply that until it converges. Yeah. 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 Question. How do you?
Is there any method that can guarantee to find the global optimization?
So you're asking, is there any way to guarantee that you get to a minimum? Well, if you assume your function is convex, then it's going to be shaped like a bowl. So if you want to visualize it, then it's like this. So this is an example of a visual of a convex function in 2D. So it's like f of 1, 2. So if the function, when you plot it in 3D, looks like this, then gradient descent will go from some point that it'll make progress towards the minimum, assuming your step size is small. If it's too big, then maybe not. So, but if you have some arbitrary function, then they're usually not convex, so usually you can't make a guarantee. Yeah. Any other question? Yeah.
So is it possible for us to verify what we found almost every local? So if the whole process is random, you just randomly put the ball on the surface. So is it possible we may ignore some certain local medium on the product?
So are you asking, is there a way to guarantee that there is some local minimum in this case? Well, yeah, that's the Hessian, right? So you would compute the Hessian if it's positive semi-definite or positive definite, then the function would be shaped as like a bowl. And so you would get like some kind of local minimum. Yeah. But I mean, in general, if you don't know anything about the function, it's hard to make the types of guarantee. Anyway, yeah. So if you want more, you can probably look at this video. I mean, I think again, most of you have seen the YouTube channel, so yeah. Yeah, I mean, I put in a link in the reading, in the quote reading for today's lecture, the link to one of his videos. So you can just look into that if you want more. Oh, right. So we've been talking about things like gradient descent, but without really thinking much about constraints. Okay, but when we are doing optimization in practice, you will be using constraints, right? Because you can't just normally optimize something without considering constraints. Like if you're trying to optimize your company's budget, you have like optimizing your company's revenue, you have like budgetary constraints for most of you anyway. And yeah, so many problems in engineering, they're defined as a set of constraints defining the feasible solution. Then you have a cost function that is the overall quality of a solution. And then this cost function is the thing that we are trying to minimize, like you minimize your overall cost subject to your constraint, like g of x. And generically, because we write it as g of x less than or equal to 0, like why is that? Yeah, because if the constraint was like g of x must be less than or equal to 42, then you would just redefine the function to be g of x minus 42 equal like less than or equal to 0 or something. Yeah, is 42 like some lucky number? I think someone told me that. Like I'm losing touch with like what you guys know anyway. Yeah, so that's why we say less than or equal to 0 by default. All right, so here's one example. So let's say that we have some fires, and this is very common in California, by the way. We do have a lot of wildfires, and if you have different fires that might need respectively, 1,000, 2,000, and 3,000 units of water to clear, and then you have two aircraft, A and B, that can deliver respectively 1 and 2 units of water per time, then how do we frame this in terms of a constrained optimization problem? Well, so the objective here is to try to extinguish all the fires in minimum time. That seems like a good objective. So if you have time t, then we want it to be small, right? But it's got to be you minimize t subject to something. Yeah, so if you want to write it out more formally, then you would have like TA1, TA2, and TA3 be the time that vehicle A devote to fire 1, 2, and 3, and then something similar happen with vehicle B. So like, what are some examples of like, how do you write out the constraint here? Like, let's just assume we have minimize t, but then what goes in the subject to? And Yeah, question, yeah. All right, so you talked about T1A plus TA1 plus TA2 plus TA3, right? You talked about the sum of them. What are they equal to? Less than or equal to 1? Oh, so you said less than or equal to 1 for both. Okay, I see. Yeah, so you would, well, I think the way that I would frame it is something close. So I would frame it as, you know, you minimize time, but you have, it's sort of like you have two aircraft that are operating. So you want to be able to minimize T, but you need your, like the time, the total time that the first aircraft operate, it's gonna operate, then you have, the 3 times, right? It has to be, yeah, less than or equal to T because and then you also need the time that the other aircraft had, like to be less than or equal to T, right? The other constraint that I would add are you need the time that you have for A1 plus 2 times the time that you have for B1 to be equal to 1000. So if you want to extinguish fire 1, which need 1000 units of water, then these are like unit time, but because if you have the unit time, if the time is like 1, you get 2 units of water from the aircraft B, and then you get 1 unit from aircraft A, and then you need this value to be 1000. Yeah. Then something similar will happen with with fire 2 and then fire 3, which have different target numbers of units of water that you need to extinguish the fire. And then, yeah, some other constraints are like you need T to be greater than or equal to 0 because you can't have negative time, and you also need the same thing for the individual time the 6 individual time variable that you have. Yeah. And so again, this is one example of some kind of optimization problem and like how we would write out the constraint. Yeah. So any questions about that? All right. So here's another example of an optimization problem. You minimize the sum from u of t, so you have 3 terms, so u0 plus u1 plus u2, subject to these constraints. And again, like this problem, like I don't think this is the problem that anyone would care about. It just meant to show you like what it looks like. So it's like some example for you to see how to formulate it. If you want to rewrite it, this is the same way to rewrite it, but it's a little bit more written out a little bit more explicitly this way. Yeah. Yeah. So what value of u would well, I guess what 3 values of u would minimize this thing? So if you try to solve this, you can try to punch in the numbers yourself and then try out different things, but that becomes a little bit difficult to do, especially when you get to more complicated functions. So you need like principled algorithm to try to do this. Yeah, but if you look at this long enough, you can try out different values, and then what you might get is something like this. So if you have something like this, you have U0, U1, and U2. Their sum is 2.5. Now the constraints here show that you have x0 equals 0. So if you look at the first equation, you get x1 equals 0 plus 2.5. Then you get 2.5. For the second equation, you get x2 equals 2 times 2.5, which would be 5, and then plus 0, so that's 5. And then x3 is 2 times 5, which is 10, plus u2, which is 0, and then that's the constraint that we wanted. Yeah. So again, you can try to verify this, but we also need a more, a principled algorithm to be able to handle this in general. Yeah. And more generally, if you think of f and g as being affine functions, the affine is another way of writing out linear, but in higher dimensions. So if you have like a matrix A, then the x, like A times x, where x is a vector, then it's like still considered affine because it's linear with respect to x. Like if you had x transpose times A times x, then it would not be a linear function anymore because it would be like a quadratic bowl in n dimension. And yeah, when you have these types of problems, they're considered linear programs, so they're a specific type of optimization problems that are easier to deal with because if you have linear function, they're usually easier to deal with than like nonlinear function. Like kind of like how Gaussians are easier to deal with than other types of function too. Yeah, and then a standard form for writing out a linear program might be you minimize. I mean, it says min, but no, I prefer using minimize because that's the thing that we're trying to do. So we're trying to minimize this whole thing, like C1 x1 all the way to Cn xn equals z. So what's the optimization variable here, by the way? Like you're minimizing what here? Like what's the variable that we minimize here? Yeah, it's x, right? So C is just a constant, right? So the thing that we actually care about is the x, subject to these constraints. So you might write them out like this. So these are all like, again, linear functions. How do you write them out in a matrix form? I mean, you can write a linear program like this, but like if you're on like your exam, then you have limited time and space to write out your answer. You probably want to write out in matrices, right? So, yeah.
Well, for the minimum C1 x1 plus C squared and so on, that would be C transpose times the vector x, and then for the other one, it would just be A times the vector x equals the B vector.
Yeah, so I think that's basically what you were mentioning here. I also added in I added it in the x greater than or equal to 0. Like that one is more like, I guess this is not, you don't always have this, but if you're optimizing something that is positive like time, then you would have something like that. Yeah. So this is another way to write it out. Yeah. So I should have been a little more clear about the x greater than or equal to 0 thing, but yeah. All right. Yeah, and then so one way to try to approach this problem is by using an algorithm known as the simplex algorithm. So we're not going to go through this into too much detail, but we will at least show like the intuition of how it might work. So we have two variables, x1 and x2. Those are the things that we are trying to optimize. Let's say that this is our optimization problem. We are trying to maximize x1 plus 2x2 subject to the constraint of x1 less than or equal to 3, x1 plus x2 is less than or equal to 5, and x1 and x2 are both non-negative. So one way that you can think of the intuition here is that every time you have a constraint, you sort of like block out regions of the plane that are invalid. So if you have x1 and x2, they must be greater than or equal to 0. And so you would just shade in this this area. And then if you only have these constraints, then this is like the region of valid x1 and x2. Are we done? I put in 3 constraints, so we only did one of them, right? So if you have x1 is if we require that x1 is less than or equal to 3, then which one is the valid one, left or right? The left one, right? Because we need x1 to be less than or equal to 3, right? And then if you have the second one, you need x1 plus x2 is less than or equal to 5, and then that would result in this shape being the set of valid points, right? Because if you have this point, this would be 0 plus 5, that is 5, and then if this extended out a little bit further, you would get x1 equals 5, and then you just have this like linear interpolation here of the line. All right. So the intuition here is that this thing will describe the set of possible x1 and x2 that satisfy the constraint. But now we have to maximize this. And the way that you can do this is you look at this function here. This is our two-dimensional function. What you can do is you can take the gradient of that function, which describes the maximum rate of change in the function. And if you do that, then like, what's the gradient here, by the way? It's a function from 2 dimension to 1 dimension, so the gradient is 2 dimension. Yeah. And then if you do partial derivative with respect to x1 for the first term, you get 1, and then you get 2 here. So it's like 1 and 2, right? So if you plot the gradient, the function looks something like, well, this is a little bit, it's not drawn to scale. It looks something like that, but the key idea is that like you get to 1 unit here, then you get to 2 units here. So it's like 1 by 2. Yeah. I mean, the way it's drawn is like, it looks like it might be like 1 by 4, but it's really 1 by 2. Yeah. But I think the point is that this function is basically, this gradient term is pointing in the direction where you have like the most increase in the function value. And the way that you try to do this algorithm to try to optimize the value of this z here is you follow the gradient and try to sort of go in that direction, subject to like being in the region where you have your constraint, right? Yeah. So if you're, yeah, so I guess the intuition is that if you're not at a corner, then there's always a direction you can go to improve the function, or at least like not make it worse. So yeah, so if this thing is pointing here, then you might as well just like go here because like the function is going to be pointing more in that direction. Yeah. Yeah. Again, this is not really meant to be rigorous. It's meant to be just to give a sense of like what this algorithm is trying to do. Oh yeah, so yeah, so when does this not hold? So when does it not hold when does this condition here not hold? Um, Yeah, so what happened if we're not in a linear program anymore? Like what if these functions are non-linear, then you don't end up getting the type of structure anymore. Yeah. So yeah, I think we're gonna cover that after a short break first. So I think we'll give you like a 5-minute break for now, and then have a good break, and then we'll get back in like 5 o'clock. So I'll let you think about it. Yeah. And in that time, you can also probably watch one of the 3 blue, 1 brown. Is it blue or brown or brown? Yeah, blue, brown. Yeah. Yeah, it's 3 and then 1. Yep. Oh, we're covered. Yeah. Oh. Yeah, I'll try to, I think the reason for not, opening the solution is because like, the risk that some students will take the solution and then they share it with other students for the next year, so a lot of coding down that all the things right now, but I think if you have I think if you post a microphone on Piazza, I think I can try to get to what you give you what you need, yeah, and also I think for you, if there's like a discount, but I'll try to make sure there's like a full solution stack. And that's how I'll check it. But it should be, I think it's a little bit tricky for me to try to. It's always fun to be on. So when you learn that, thank you. I had a same question when I was back to that's Professor who taught me. All right, couple of seconds, so let's finish up your last few conversation. You can go ahead, you finish. What were they talking about? I don't know. Oh. All right. Well, yeah, I hope you had a good break and then. So I think going forward, I think the main thing that we'll talk about now is what happened when you have this kind of like constrained optimization, but it with a nonlinear function. And so for that, we use a method called Lagrange multiplier. It's a very common method that is used in optimization where we'll cover this in the next few slides anyway. All right. Here's an example in 2 dimensions. So we have some level set or where points here that form this line where you have g of x1 and x2 are equal to 0. So this is some kind of it's really a curve. So it's like some kind of curve. And if you have some point on the curve, then then you know like how to write out what the tangent line would look like, but hopefully it's also clear like what the gradient would look like. So you can write it out like this. So TG with the arrow on top, that is our tangent. So if you're considering this point here, then you have your tangent vector, like this is the tangent vector at where it coincides with the curve at this point, and the gradient is this thing here. So why did the gradient look like this? Like, do you know why the gradient is like this? Yeah, so the general rule is that the gradient is always going to be perpendicular to some curve that you to some level set of the function, and the reason why it's pointing this way instead of this way is that I just assume that the function is going to increase in that direction, right? So it's like what this is showing here, what this g of x1 and x2 equals 0 thing, that's like a level set. So you can think of it as if you have your 3-dimensional plane, and then like this is where you have the function to be equal to 0. So you have like some kind of curve, and then there's like some plane in there where the 2D function is 0, and then it's sort of like if you try to maybe take a top-down view, you can think of that as like part of a level curve of the function. It's a little bit easier if you have like some software that you can use to rotate and move functions in 3D. So you can look at the video that I shared on the reading the reading list for today. Yeah. And again, the reason why we often use equal to 0 for the level set is because if it's equal to some constant, you could just bring the constant over here, then you just get something equal to 0. Yeah. Yeah. And another way, yeah, sorry. So this is so this is just this example. Like again, I didn't specify the value of G here, but if you want an example where I actually show you what G is like, then you can think of this example circle. So this is G. And this is what it looks like in the Cartesian plane. And if you take the gradient of this, then the gradient would be 2x1 comma 2x2, right? Because if you take the derivative of with respect to x1 and then also with respect to x2, you get these 2 components. I mean, more formally, you should write this as really, it should really be written as a column vector, but we're just writing it as like this comma that just for simplicity. But yeah, it's really a 2 by 1 vector. All right, so if you consider this point, so this is just some arbitrary point on the plane. It's square root of 2 over 2, comma, square root of 2 over 2. So if you just look at this, you should be able to see like which direction the gradient points. So yeah. Like if I asked you to draw out the arrow that show where the gradient is, then hopefully you have a rough approximation of where the true arrow should be. Is it pointing outward or like inward to the origin? Like which direction does the gradient point? Outside, yeah. So the gradient points like this direction. Yeah. And you'll notice that it's also perpendicular to the tangent of this contour. Because the tangent line would be like something from here to here. And then the gradient is just pointing yeah, outward. Yeah. And again, the reason for that is because like if you like this is where the function increases. So like if you're increasing the value of x1 and increasing the value of x2, like you just make the whole function I guess you make this thing just increases. So and what we often do, what we might do when we use the function g like this is define this as our constraint, and then we have some arbitrary other function that is our objective, and we want to make sure that it lies, our candidate solution lies within the circle when we try to optimize some function. Although when we say that, what's gonna end up happening normally is that the value that optimizes something is gonna be like near the border of this. Yeah. So but anyway, this is just again one example of this is a function, this is the gradient, and then here's the arrow where it points. So if we go back to the function that we have been using as an example, we have considered this as the tangent line, and then this is the gradient, which is perpendicular to the tangent. You can write it out like this. Now, if you consider some other function, so let's say f is some other function, right? Now, so we just put in a random like arrow. Okay, we didn't actually put in a curve for the function f. So the curve for the function f we don't show here, but it's just this is just some other function. It's gonna in our context describe what is the objective function. We're trying to minimize this or maximize this, but if you're maximizing, just make it a minimum by negating it. But while this is true, usually this is non-zero because like this is some arbitrary f, but then if when we evaluate it at some point x1 and x2, like I didn't show this in the notation, but really this should be the gradient of g at some x1, x2. But for notational reason, we just ignored that here. Yeah. And so we will normally have g be our constraint, and then f is the objective. Now, if this is 0, like if this is true, then what happened there? No. So if both of these conditions are true, then what happens is you get, you know, you might get your gradient like this, and then you might get f, which is what the and we really have to put in the same input here, so that is the same input here. But when we write something like that, that just means that at the given point, then the gradient, they coincide, but they're off by some constant value, but they do coincide otherwise. And this is the tangent line. Then the two gradients are perpendicular to this point. I mean, if you have a different, if the tangent, if you're considering like, this point here, then the gradient would just like be pointing this direction. Yeah. Again, this is assuming again that the function value increases when you go this way. You could also have this represent like the top-down view level set of a function that curve that increases when you go inward to like this. That would look like that would look like this, where the function value increases this way. So what you can do is you can write out, because you have something like this, you have your two equality, you can set them equal to each other subject to some kind of a constant. And what do we write for that constant? Lambda, yeah. So yeah, we have gradient of f, really f of x and x1 and x2, but we're just assuming that they're evaluated at the same point. So if what we can conclude is that we have gradient of f plus lambda gradient of g equals 0, because they basically just point in the same direction, but they're off by some constant too. And in the context that we care about, again, like G is some kind of constraint. Like if this is a constraint in 2 dimension, that means we only want to consider values of x that are like within the constraint. And then f is something arbitrary. And then if f increases when you go this way, you try the optimization problem that we care about, like bringing the value of x1 and x2 like in this direction to increase the value of f, but you have to stay like within the constraint. Yeah. So if you look at the video that I linked to, that you'll see some visual examples of like how it works more. Because like it's hard to like draw it out on the whiteboard, on the chalkboard. Yeah. Yeah. I don't like chalkboard. Yeah. Question?
It's like you said that, if that's all we know, moving along the tangent usually increases or decreases fx of n y or fxy. Oh, what's the case where fxy will decrease as we move along the tangent? Would it be, maybe, can it be drawn out here? Or
Yeah. So I guess like, are you so are you asking more about the text that I wrote here? Like, what? Yeah, moving along the tangent usually increases or decreases. Yeah. Well, I mean, you can. I guess what I meant. I guess what I meant here is that normally if you have some arbitrary function and then change the input, you're going to change the output of the function. I guess that was basically like a very generic, almost always true statement that I wrote. Maybe it's a little bit confusing the way that it's over here. Yeah. Basically, that statement is just saying something that's almost universally true for any function. Yeah. 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 So the way that we end up deriving what we then call the Lagrange multiplier is that we try to define the set of points where you have g of x1 and x2 is equal to 0, and then you have this thing true, and we redefine a new function. We define a new function f, which is the set of three inputs, so you have x1, x2, and a lambda value. And the way that you decompose this function is that you have f of x1 and x2 plus lambda g of x1 and x2. So this is a way of like repackaging all of our input into one equation. And the reason why we have this is that like if you end up taking the derivative, you like end up with like this thing here, right? Yeah, so like it seems like it comes out of nowhere, but if you look for the input value such that the gradient of this is 0, then you'll basically derive like what this equation is. Or like actually like both of these equations basically. Yeah. So what is the gradient of f? Like how do you write out the gradient of f? Well, what is the dimension of it? 3 by 3? 27 by 1? What's the dimension of the gradient? Is it, oh yeah, what is it? I thought I meant like what's the dimension of this thing, gradient of f? I wrote this as 0, but this is not necessarily a scalar. Yeah.
Since it has three inputs, or x1, x2, and lambda should be 1 by 3, maybe? Like a whole vector of x1, x2, and lambda.
Yeah, I think you got it. I think you got it, but it's 3 by 1. Yeah, so everything, when we work with vectors, they're column vectors by default. So the dimension of a gradient, because this is also a real valued function, right? You have f of x1 and x2, that's a real valued function. G of x1 and x2, that's another real valued function because it describes a single cost or a single like, cost or some like a constraint thing. And then this thing is has 3 input and then there's a single output, so the gradient is like 3 by 1. And if you compute each individual item in it, well, I mean, if you look at the left is how you actually define like what is the gradient. And then to the right is just how you compute it. So does everyone see like how to get to this point? I mean, there's not much you can do because if we only tell you like here's f and here's g without telling you what they are, then you have to stick with f and g here. But you can still do things like the partial derivative of f with respect to x1 is partial derivative of f with respect to lowercase f with respect to x1 plus lambda partial derivative of g with respect to x1. And the same thing here, and then for here, because we take the derivative with respect to lambda, we get rid of the f. Yeah. So this is what it looks like when we say that the gradient of this thing is 0. Yeah. And notice that notice how this relates to this, right? So you have g of x1 and x2 is equal to 0. And then that's the same thing we have here, right? And this thing here is basically this thing here. Yeah. And formally, we will call f the Lagrangian, and then lambda is the Lagrange multiplier. All right, so let's do an example. So find the extreme value of a function f of x1 and x2 equal to x1 times x2. So it's a real valued function from 2 input to a single like output. So the gradient is well defined, it is 2 by 1, subject to this constraint. And then you have g of x1 comma x2 is equal to this thing. again, I don't think anyone cares about this problem in practice. It's just a way to give you like, here's an example of how to use the Lagrange. So, how do we get started with this? So you take the partial derivative of something and then you set them to equal to zero, or
Yeah, we can find the like the points for gradient that way then we take this like the
hmm. Yeah, so I think the first thing I would do is first draw out the Lagrange. So that is this thing here. So if you have a constrained optimization, you could just draw out, like, you can just write out here the Lagrangian. Then you can try setting the gradient equal to the zero vector really. Yeah. And it looks like this, right? That. Everyone see how we got this? So like for the first one you have, because if you take the derivative with respect to x1, then x1 and x2, like the x1 goes away, so you get x2. Then here the 2 goes down, and then you get x1 divided by 4, then the other terms go away. But we still have the lambda here, so that is x2 plus lambda x1 divided by 4. Right. And then yeah, the same thing for this, and then the third one is usually the easiest one because you just get rid of the lambda, then keep g. So, and then you make it equal to 0. Again, it looks like a scalar, but just interpret this as a 0 vector. Because sometimes we don't bold it, and then especially when you're writing it out, it's hard to bold the 0 vector. So it's just understood that when you write 0, it means 0 for all 3 components. Yeah. Yeah. Yeah, and then the next thing after that, especially if you're trying to do the solution by hand, then you would solve for the 3 different variables here. I mean, in practice, you would just run it on like your laptop or whatever. But if you to get some practice with it, it's good to punch through the numbers at least once, or really at least twice, because you have one on the midterm, or you have one on the final too. So that's 3 times go do it. Yeah. So I'll give you a couple seconds to think about this. So can you try solving for x1, x2, and lambda? Uh, yeah. I'll give you a few seconds to think about it. Or just peek ahead in the slide if you downloaded them. Hmm. So we can go through some of this now. All right, so the first thing to do when you have this is, again, it's equal to the zero vector, so you have three different equations here in the, if you want to call it a system equation. And then when you do the first one, it is x2 is equal to minus lambda x1 divided by 4, then you get something similar to what's going on in the other two equations. Now, after that, then what happens here is that we plug in the value of x1. So x1 is equal to minus lambda x2. So you can plug that in here, and then you get lambda squared times 2 divided by 4, and the negatives go away because you have another -1 times -1. And then you can just, because you have x2 equal to lambda squared x2 divided by 4, you can get rid of x2 on both sides, then you get lambda squared equal 4, and then you get lambda equals plus or minus 2. So if lambda is 2, then you immediately know, like, here's the value of x1 and x2 that we would get. Like if lambda is 2, then like then x1 would be minus, like minus x2, then, which is what you get here. Like you can get like for each, for some value of lambda, you get your x1 and x2 value. And when you go from here, you can just derive it as lambda is equal to one of these two values, which will result in a specific value for x1 and x2. So you have like two sets of possible solutions to this. Another way to visualize this is in 2D when we're trying to look at how the function is shaped, and you can think of f as representing the objective function, and then these curves are different level sets of the function. So this curve here represents c equals 1, right? Because if you look carefully, there's 1 and then there's 1 here. And then if you multiply them together, you get 1. And then that's this value. That's this value here. And if you go along the curve, like if you go here, that is 2 and 1/2. So 2 times 1/2, that's also 1. And then, so this curve here, the one that I am going over here, that's like, the level set of the function where it equals 1. And if you want the level set where it equals 2, then you would just jump over here to like this other curve. Yeah. Or you have, 2 times 1 is 2, and 2 times 1 is also 2 here. Yeah. So again, one way to think of it is you have your function f, you're trying to increase it. So like you move in the direction of maximum increase, and the function subject to some constraint, which constrains the location of where your values of x1 and x2 can be. And so you would have to be like within this constraint. Again, that's just for a particular constraint. Like if you're working with a specific problem, you'll likely have different constraints that you'll deal with, and then your curve will look a little bit different. Well, this is roughly the visualization of how this would look. Yeah. And one application of constraint optimization is something that we call inverse kinematics. So inverse kinematics is the robotics problem of, given a desired position of the robot end effector, find the values of the joint angles that are within the limit and which avoid collision. And for more details, you can just see the next few classes. And by the way, inverse kinematics is something a little bit more broad. So you can also have inverse kinematics for like human joint in simulation. So you can have like biology inverse kinematic where you have a simulated human, and then a human joint, like the hand will move in someplace, and then the simulation will have to figure out where are all the rest of the joint of the human that have to move, or how do the rest of the joint of the human have to move to make the, to make that target joint move appropriately? Because when you're dealing with a robot manipulator, you can't just say, move the gripper to this arbitrary position. In fact, most positions are not going to be valid for the robot. Like if you try to make the robot reach, if you try to make a robot manipulator reach to a target that's like outside of it, like reachable, like workspace, then you can't do it. But for some locations, you can do it. And then the task is, you want the like gripper to go somewhere, but then you have to figure out what are the joints of the robot that have to, what value do they have to be so that the robot's gripper is, at your desired location. Yeah. All right, yeah, so a quick summary of today. So we cover some basics of math programming. So we covered like things like finding the minimum of the function, derivatives, gradients, Hessian, a little bit of linear programming, the simplex algorithm, and the Lagrange multiplier. Coming up next, we will cover configuration spaces. So that's a very fundamental topic in robotics. So this is extremely important to know. So we'll see you next Wednesday then. Not next Monday because there's a holiday. I think we're celebrating the president. So yeah. Yeah, so I'll see you next Wednesday then. All right. That's it for today. Thanks.